Gradient descent. In likelihood-based classification, the parameters were the sufficient statistics of a P of x conditioning on Ci and a P of Ci, and the method we use to estimate the parameters is maximum likelihood. In the discriminant-based approach, the parameters are those of the discriminants, and they are optimized to minimize the classification error on the training set. When W denotes the set of parameters, and the expectations of W conditional on X is the error with parameters W on the given training set X, we look for W star, which is equals to the argument of minima of the exponential of W conditional on X, where the minima is taken among all possible X, and in many cases, some of which we will see shortly, there is no analytical solution, and we need to resort to iterative optimization methods, the most commonly employed being that of gradient descent. When e of x, the exponential expectation of w, is a differentiable function of a vector of variables, we have the gradient vector composed of the partial derivatives. That is, delta w of e is equals to the transpose of the following term: delta e divided by delta w1, delta e divided by delta w2, and so on to delta e divided by delta wd. And the gradient descent procedure to minimize e starts from a random w, and at each step updates w in the opposite direction of the gradient. Delta wi equals to minus rho times delta e divided by delta wi for all I, and wi equals to wi plus delta wi, where rho is called the step size, or learning factor, and it determines how much to move in that direction. Gradient ascent is used to maximize a function and goes in the direction of the gradient. When we get to a minimum or maximum, the derivative is 0 and the procedure terminates. This indicates that the procedure finds the nearest minimum that can be a local minimum, and there is no guarantee of finding the global minimum unless the function has only one minimum. The use of a good value for rho is also critical. If it is too small, the convergence may be too slow, and a large value may cause oscillations and even divergence. Throughout this book, we use gradient methods that are simple and quite effective. We keep in mind, however, that once a suitable model and an error function is defined, the optimization of the model parameters to minimize the error function can be done by using one of many possible techniques. There are second-order methods and the conjugate gradient that converge faster at the expense of more memory and computation. More costly methods like simulated annealing and genetic algorithms allow a more thorough search of the parameter space and do not depend as much on the initial point.